So first of all, as Ed has already indicated, never has the pace of change in our industry been faster. And I've seen more changes, whether it's in the supplier community or emerging technologies, in the last 2 to 3 years than in all of my 35 years working in the electronics industry. So this pace continues to accelerate. But as an engineer and as a physicist, maybe we shouldn't be surprised if we think about this, and I guess you're all familiar with this. This is the second law of thermodynamics. Basically what it says is most of the time, in fact almost all the time, entropy is increasing. It's really hard to keep entropy steady state. It's always increasing. And for entropy you could substitute chaos. And that's what's happening in the universe, that's what's happening in our industry, is there's more and more increase in entropy, increase in chaos, increase in options, increase in choices in terms of the way we do things. So enough of the theory, and what Rob asked me to do was really kind of give my view from a design engineer's point of view of the different trends within engineering, within the market that impact the way that design engineers need to think and need to work today. So the first one is integration. So we've had 50 plus years of Moore's Law, which is just driving increasing levels of integration. So that level of integration feeds into the next trend, which is moving from designing for just parts to designing with full solutions. And then when you add on top of that connectivity, that enables a whole load of other techniques and approaches to engineering that didn't exist before. And when you connect everything, you end up with a lot of data, big data. The consequence of these, and each of these kind of drives into each other in a sequence, but the consequence is an increase in complexity of end systems, and therefore of the design skills and requirements to design those systems. The last one which I wanted to put on here is consolidation. And I quite like this graphic because it illustrates really nicely. This could be the Freescale fish, this could be the NXP fish, and then this could be the Qualcomm fish. So the NXP fish hasn't actually finished digesting the Freescale fish, and the Qualcomm fish is coming along behind to gobble it up. And you all know from an obsolescence point of view the implications that that has, because these consolidations and these mergers and these acquisitions really happen for one of two fundamental reasons. One is to build scale, and the other reason is to gain technical synergies, extra technical expertise that complement an existing portfolio. Or they're somewhere between the two. They're somewhere on the scale of the two. Now both of those have implications from an obsolescence point of view, because if it's technology, it means that that's a company that wants to innovate, that wants to bring out more differentiated, sole source products that may or may not still be around in 2 years' time. If it's a scale integration, then that's code for we need to take cost out. And that means that those suppliers will have less resources to support us. It also means that those suppliers will look much more closely at their portfolios and say, where do we have duplication? And they will remove duplication. And they will say, where do we have product lines that are less profitable or not profitable? And they will stop making those products. And they will not be as rigorous or robust as they have been, because they have so many other things to do about the process they do that. And that has obvious implications in terms of the end of life of products and for our industry. Finally, before I move on from this, I just wanted to point out some key words on here, because for those of you that are playing bullshit bingo, there's integration, solutions, connectivity, big data, and of course IoT on there as well, so you can cross all those off, and you can maybe even get them again through the rest of the presentation. So just to go in a little bit more detail, this back in 1993, as a techie guy, these were the state-of-the-art gadgets that I owned. And this is kind of 25 years into Moore's Law, because these will be designed in the early 90s. And you can see that they're all portable, they're all battery powered, and they were enabled by Moore's Law allowing the integration of the circuits to consume less power. They were also enabled by the development of very sophisticated battery techniques, technologies that meant that they could be made portable, and they were also driven by the evolution of more sophisticated display technologies as well. So those things came along, and you're pretty proud if you had these, and they were very slick pieces of engineering. If you take the Walkman, for example, they carefully designed that it was just a little bit bigger than a cassette. And you could store, if you were careful, you could get maybe 40 tracks on that, if you were careful about the way you recorded it. But that was a big step forward from what it was before, but it was also designed within the constraints of the cassette. So Sony thought they'd cracked it. They designed a great bit of kit because it was only a little bit bigger than a cassette. Well, the next step, of course, was that the storage medium then got smaller as Moore's law went on and on and on. So if you roll that forward 20 years, all of that was replaced by this gadget that I had. I put 2013, the first iPhone was actually 2007, the first connected iPhone on 3G was 2009, but Arrow being Arrow in those days was a little more conservative, so I didn't get my hands on one until 2013. But that is 20 years. If you just take a step back, cast your minds back, depending on how old you were, to when you were a little boy or a little girl, and you thought about, in 20, 25 years' time, what will technologically be possible. And I would never have dreamed that all of that stuff on the left could be done by the device there on the right, on my right. So from parts to solutions. So when I started designing, which is around 30 years ago, 35 years ago, I worked at a company called Ferranti that some of you may remember in the defence industry. And on my first day, I was given not one, but 3 A4 size folders full of sheets, and they were dumped on my desk with a big thump, and the dust flew up. And I was told, this is the Bible. This is the standard components manual, volumes 1, 2, and 3. Everything you design must use a component that is in there. They're all triple sourced. They've all been checked. We've taken the drawings, we've redrawn them, we've respec'd them, we've checked and matched the specs, we've checked the sources. You use those. If I wanted to use another component, let alone a sole source component, I had to jump through hoops of fire, I had to leap barriers, I had to sign my name in blood that we would be able to redesign that product. That was because back in those days, everything was at a component level. The library of components was much smaller. They were manufactured by many people. We had a much more fragmented industry. People were able to exist in a competitive market around commodities. What progressively happened from then was more and more sole source, differentiated devices being developed. And every supplier wants to have ideally 100% portfolio of differentiated products, which makes from an obsolescence point of view the job much harder. So you've got this tension between, do I use the latest, most innovative products, or am I a little conservative, and I design my system with redundancy, with duplicated sources that I can make sure I can make it. And that tension has moved much more towards, let's go with the innovative, free-flowing way of using sole source components. So the consequence of that is now that the design engineer, on one part, will design with components, and the physical interface, the analog interface to the world is still very, very important. And the role of the design engineer is still very, very important. Because it doesn't matter how much data you've got if the data is no good. And it's usually component level design at the front end of the node, which is where you need the nose of a good hardware design engineering team. However, there are far more options now for that engineer to make the decision, do I knife and fork this, or do I go and buy it? They can buy a SOM, they can buy a single board computer, they can buy a COP solution, they can buy their power supply off the shelf, or they can do some of the design themselves where it's important. So from a design engineer's and system engineer's point of view, it's really important to think about where does it make sense for me to go and buy something that somebody else has done the majority of the work and invest my time translating my company and my IP into the uniqueness of that product and doing that design. So those are choices I never had to make when I started out as a design engineer that modern day engineers do. So the next one is, and it's in my contract, and I have to put IoT up on a slide at some point, so this is that slide, and I'll let you read the number of nodes, but it's basically predicted, and it looks like we're on track for this prediction to be 50 billion connected devices by 2020. And that's more significantly more than there will be people at that time. And these predictions started off, kind of 5 years ago, and they seem to be tracking out to be pretty accurate, and actually maybe even conservative. The key one here I wanted to highlight was that bottom note, which is what this drives is a whole raft of different standards on connectivity. So 3 or 4 years ago, people would be talking about LoRa and Sigfox as emerging techniques. We had 2G, then we had 3G, then we had 4G. Now we're talking about NB-IoT, Industry 4.0, Wi-Fi, BLE, low power BLE. If you're an engineer, where do you go? What do you choose? You want to make sure you choose the VHS, not the Betamax. In fact, you probably want to make sure you don't even choose the VHS, because that's probably going to disappear at some point. So it's even more choices, and these aren't hardware choices. This is where a design engineer is having to work with the system engineers to make decisions around things which are no longer just to do with hardware. So you can start to see the proliferation of areas and scope that a design engineer has to work with today. And I have to say, we're just not paid enough for that choice we have to make. So, big data, and I think you're going to hear quite a lot more about this, but whenever I look at statistics on this, and I can tell you that if anyone else puts numbers up that are different, mine are right, because I checked them on the internet, so they must be right. So, the one that gets me is this last one, is that there has been more data generated in the last 2 years than since man first stood up and started walking, up until that date. If you just stop and think about that, forget the number of zeros after the data, but that is just a phenomenal amount of data. It's too much data. Edward spoke about that fact that is too much for us to cope with. So it's how do we intelligently actually choke down that? In fact, if we remain with the current communication standards, we will not be able to get that data into the cloud. So there have to be more intelligent decisions made about what do we process at the node, what do we process at the gateway, and what do we process in the cloud. How do we make sure we don't filter out valuable information, but we filter out the FUD before it gets there? So big implications from big data as well. The next one is about complexity and complication. And I just want to take a second to stop and think about the difference between complexity and complication. So the increase in complication of chips to multi-core 64-bit processors that fly at the speed of light in terms of the computation, they're complicated. Sending a rocket to the moon or to Mars is complicated. There are a lot of systems involved, but they're all deterministic. Every one of them has a user manual. You can work that problem out given enough time. But it does take a lot of time, it takes a lot of energy to do it. Complex systems involve other factors that you can't control. Maybe economic factors, maybe social, maybe political factors, maybe something to do with the weather. So on the user manual analogy, bringing up a small child, and I brought 3 up, and they turned out completely different, that's complex. I haven't yet found a user manual for a child. And this is important because from an engineering point of view, engineers think in a very linear, very logical, very process way. You cannot solve complex problems with engineering, with mathematics, and more importantly, on your own. So, just a few facts around the amount of lines of code in different pieces of gear. So a modern fighter jet, the ones that are out there today, has got around 2 million lines of code in it. And that's because designed to be very safe, but actually designed around the turn of the century. A modern passenger jet, designed probably 7 to 10 years ago in terms of when the code was written, that's gone up to about 7 million lines of code. I'm actually not sure how comfortable that makes me feel when I get one of those, but they seem to be working out okay. If you wind that forward now another 7, 10 years, and you're looking at the connected car, which is the latest thing where code is embedded, it's hard to get to the data, but the Mercedes S-Class even has more than 100 million lines of code. 100 million lines of code. And the Tesla there, the estimate is these cars will be producing 4 terabytes of data a day. Some of that will be consumed and confined in the car, some of that will be transmitted out to the cloud. Again, you can see where this data explosion comes from and the complexity of those systems comes. And with that complexity, needs more effort. So this chart here, which I'll reveal in a second, shows that. So just as a statistic, out of all the engineers graduating and coming into the industry nowadays, 4 out of 5 are software firmware engineers. 1 out of 5 is a hardware engineer. So this shows where a lot of the energy and a lot of the effort is going. And from an obsolescence point of view, we've always focused purely on the component and the hardware side. Historically, increasingly nowadays it's around the software. And when you look at the effort required, every time you double the amount of code, they reckon that the complexity of that design goes up 4 times faster. So 8-fold increase in complexity for a doubling the code. The next factor is the rise of the platform economy. And most of us will be familiar with these platforms, Amazon, Airbnb, all of that. But remember where Amazon came from. Amazon started off as a website where you could buy books, and then they added CDs because they were easy to store, they were easy to catalogue, they were small, they were light, they were easy to ship. Think now what Amazon does by reinvesting that money and building their platform. You can buy anything on Amazon. You can get it shipped the next day, you can even get it shipped the same day. Soon they'll be able to drop it by drone to you. They stream video content, they stream audio content, they produce video content. You can buy professional services through Amazon. You can get cloud services through Amazon. It's a platform. They created a platform when you go in on it, and it's a one-stop shop for just about anything you want to do in your life if you choose to. You never need to go to another shop. And there are emerging platforms in the innovation and design space, like Hive, who can broker anything you want to do from a design point of view. Actually, from Arrow is a platform company when you think of all the sister companies that we have and all of the services that we can provide. There's also a proliferation of community hardware and software resources. So an engineer is no longer alone. And there are tools to enable that. So if you think about Raspberry Pi, I think that's a fantastic thing. It's really democratized hardware design. Now, my son-in-law is a geography graduate, knows nothing about electronics, yet is designing with a Raspberry Pi for fun. So there's all of these facilities that will help engineers. And there's an enormous community of makers, designers who are out there, and in the same way as you collaborating yesterday with each other, they're working and they're collaborating together to share knowledge and to share best practice, because everybody can be successful. They don't want to be like the Dutch East India Company. So what are the implications when we pull all this together for engineers? Well, it's never been more complex for engineers, and they've never had more choices. And that's a double-edged sword. It's a good thing and it's a bad thing. It gives a lot more options for them to work with. We've seen these complex, yet very capable ecosystems emerge. Getting products produced quicker has never been more important. And then finally, there's never been more uncertainty around component longevity and obsolescence. So that's kind of, if you like, the problem statement and some of the opportunities. So, kind of here's my view, and I'm not an obsolescence expert by any means. I come from a design engineering background, so my observations are based on how, as an engineer, I work today compared with how I worked in the past and how my customers' engineers work. I like to think of it as a Rubik's Cube, and this is very easy to solve because it's all one colour, but the first fundamental is informed component selection will always be a fundamental. That will never go away. The second one is we need to make sure we take a holistic black box approach. So intentionally that's a Rubik's Cube black box because you can flex it and you can spin it. The important thing will be, as it is for components, is really, really rigorous and precise specification. What are the inputs? What is the transfer function of that black box? What temperature range does it have to work in? What power consumption range does it have to work in? Because when you get to that point, it doesn't matter what's in the box, as long as it fulfills that function. So it's the mindset of taking obsolescence as a view from component level to a mixture of component level, subsystem level, and even system level. And to do that, you need to use the range of all of those solutions and opportunities and communities and resources and tools that I described before. The final thing is that IoT can be an enabler. So you can connect boxes, whether it's locally within a factory, whether it's remotely, so you can diagnose what's going on, and you can update them securely and safely. So actually, if you design that box really smartly with enough processing power and enough memory and enough functionality on the interface, you can reconfigure. So you can increase the longevity by enabling and connecting your device. So I think the future's exciting, challenging. I think there have never been more opportunities and ways of skinning a rabbit, as we would say in the UK. And with that, I thank you.